But what the NSA was excited was, and I think I need to sort of speed up, NSA was excited about was that I showed that the inference problem was unsolvable. There are situations. And in order to do that, I constructed a specific example. And there's a paper there. You can read everything from the paper. So essentially, this example is such that this is the function. This is the privacy function I designed. T is the cleanest predicate. WE is the eth recursively enumerable set. And the major result here is that I proved that the eth recursively enumerable set is many one equivalent to this particular privacy problem. And by showing that, because there has been existence, Post and other great mathematicians have shown that there are recursively enumerable sets that are non-recursive, then it automatically shows that there are non-recursive, recursively enumerable sets by which you can conclude that the privacy problem is unsolvable, or equivalently stated, the inference problem is unsolvable. So once we got this result, and everybody was really excited, and then they started funding efforts on computational complexity of the privacy problem. And I did some work, not a whole lot, but because of lack of time, I'm going to move to another major contribution I made at the time in the 1990s. And that is, and our department at Gopal Gupta is an expert. I'm not claiming I'm an expert in logic programming. He's the expert in logic programming, but I knew enough of logic programming, at least at that time, where I said, okay, let me look at, because we know the problem is unsolvable. The relational databases, developing everything in C was kind of a bit of a mess. So I said, let's try to integrate logic programming with secure databases. And then I said, okay, why don't we develop a secure logic programming system and do query evaluation? Remember, there is a very close correlation between relational databases and logic programming systems. So I designed a logic, NTML, non-monotonic typed multi-level logic. And it extends type first order logic to support reasoning in a multi-level environment. Again, multi-level means everybody can have different clearances or different levels, different segments. This can be applied to role-based access control today, and I'm going to talk about that, some of my current work today. We develop both proof theoretic, model theoretic approaches, and security constraints, which are essentially security policies, are treated as integrity constraints. And we developed efficient techniques for policy processing. And we designed and developed, patented a logic program. So we implemented this whole thing, Gopal, in Prolog. And we patented the system, also licensed to Nathan Myhrvold. So what is this? Okay, so you can read this couple of papers. So these are the Computer Security Foundation's conference. So as in any logical theory, NTML has a logical axioms, a set of proper axioms, a set of inference rules. In the proof theoretic approach, we view the multi-level database as an NTML theory whose proper axioms are elementary facts and some general laws. And so the whole thing comes to query evaluation. Query evaluation then amounts to theorem proving. Now, this is something I invented this only for secure databases. This work for non-secure databases or ordinary databases was done by Harvey and Galea and all those guys, and Kowalski and so on had developed logic programming systems. So I took their systems and incorporated security and reasoning across security levels. Okay, so the two papers I described have explained this in detail. Okay, so I'm really was proud of this work as well. Okay, so now, what are the lessons learned from my early work, starting in 85, right until about 95, 96? Designing and developing high assurance systems still a major challenge. Still, because right now we have to worry not about proving, in addition to doing everything we did, we also have this whole thing that we talk about now, malware, malicious code. Relationships in databases makes it even harder. And we have to worry about malware attacks. And there has been progress on computational complexity. and defining the measures for privacy. So some progress, or the Harvard Privacy Group that Murat belongs to, is doing some very interesting work. And integrating logic programming systems with secure databases has to be re-examined. So Gopal, here is a challenge for you. Okay. So now I come to UT Dallas, and I'll talk about one area that is my work, and then very briefly what Latifa has done and what Murat, because I'm part of their team. So secure data science is something I coined, integrating cybersecurity and data science. So again, massive amounts of data being produced, securing the data, access control policies, foundations of secure data collection. So I'll talk about the foundations work that I'm doing now. Data science for cybersecurity is something that Latifa is an expert, and he got an IBM faculty award for that work. And secure data science techniques, of course, Murat is the world's expert in that area. Okay, so I'll focus a little more on the foundations. So I come here, and of course, we also have to get funding. So I talked to the Air Force, and I said, look, the 9/11 Commission report had just come out in 2004. So one of the things I wanted to, 9/11 Commission report said, if only organizations had shared data, FBI, CIA. So we wanted to develop system on enforcing policies for sharing information and determining how much information has been lost. And then, of course, there's the inference problem. And whatever we do, we have to also focus on the formal foundations, because when you talk about secure systems, it's not just like, or even process control systems. These are safety critical systems. They really have to perform, because you can't let things, things in a random fashion operate. So we applied, okay, so that was one part. So we wrote a proposal in 3 parts. The second one was applying game theory. Now, I'm not the expert in game theory, but I knew a little bit to work on that. And the third piece was active defense. So that was the original proposal I wrote, and Latifa helped me to write the proposal. And so we were very lucky for number 2 and 3. Murat joined us. Okay, so he just helped me a little bit initially for the second piece, and then took it and ran off with it. And then Kevin joined us, and he helped me a little bit with the third piece of work, and then he took it and ran off with it. So my focus is now on the first area, policy-based information sharing. So what did I do first? Remember, I had this thing, the inference problem, that prototype I developed back and licensed. That was in the 90s. Now we are talking about late 2000. So I said I really wanted to re-implement that with today's technology. So I just want to briefly, this is just some insight in passing. So I re-implemented the whole thing, focused only on query, not on updates, not on database design, but we used a semantic web. And semantic web is based on descriptive logic. And we had this, I'm not going to dwell more on this. So we developed descriptive logic. It's based on descriptive logic. We had all of these policies. And we re-implemented the whole thing. It was more of an engineering exercise. And remember, what took me 2 years in the 1990s took me only and this was my student. So, and I didn't do the implementation. The first part, I did the implementation, part of it at least. But here, the student implemented, and I think he was able to finish it in 3 to 6 months. So that one I wanted to mention. And another thing that is very particularly interesting for me, also in passing, by then we had a big contract to design the cloud. And so we said, OK, why don't we share information in the cloud, where all of us will place our data in the cloud, and then we can share the data. Of course, we need to worry about encryption. And what we did was we took the system here, and I won't say port, P-O-R-T, we re-implemented it and shared data across multiple clouds. And we did this work, and Murat and Latifa were also part of my team. We did this work with the European partners, King's College, University of London, and University of Insubria, Italy, and we demonstrated it to the US Air Force, both in the UK and US. So they got their funding from UK. So the policies, okay, so some people will criticize this, saying that your policies are kind of toy policies. Okay, I share with you provided you don't share with somebody else, or I will give it to you. I'll share with you only if you share with me, but that doesn't happen in the real world. These policies are so complicated. And that is why now we have kind of dragged Jennifer into our team, Dr. Jennifer Holmes, and so she is working, she's helping us with some of the real world policies. Okay, so now while we were doing that work, we wanted to look at a formal model for information sharing, data collection, data storage, data management, data sharing. Even our earlier work, the policies, we used ABAC, Attribute-Based Access Control, which is a NIST standard, and it's a very ad hoc standard, role-based access control. So what did we do? So we worked together with King's College, University of London, to look at formal models. And so we examined ABAC, RBAC, and one particular model that we designed was CBAC, Category-Based Access Control. And I'll explain to you what that is. It's an axiomatic category-based meta model based on rewriting systems, lambda calculus rewriting systems. And it has operational semantics from which prototype implementations can be directly derived. And we presented our work recently at ACM CodaSpy, and NIST, they liked it, but they said implementation-wise it's going to be a challenge, because if you have a model, and that's obvious, if you have a model that's going to encompass everything, how are you going to do something that's better than ABAC? What we are saying is ABAC is only one instance. What if tomorrow somebody comes and says, let's forget ABAC? And this is what has been happening. From RBAC, we go to ABAC, we go to Yukon. So what is category-based access control model? So our initial work, we started this in 2013-14. We have done the work and some of the implementation for data collection. So a category, and I'll just briefly talk about the concepts with respect to an example. Okay, you look at the papers I've listed, they talk about the actual category-based model. So a category is a class, group, domain. Anything can belong to a category. We can take two people together, a doctor and a nurse, and put them into a category. It's a countable set of, so here is from the IoT area, countable set of devices, IoT device D1, D2, a countable set of DI of data items, a set A of actions, and a countable set C of categories. Actions are send, receive, block, encrypt for data collection. Okay, so then we have lots of relationships between the entities. So data item category assignment is something, it looks complicated, but it's very straightforward. For every data item, DI, emanating from a device D, right, it's assigned the category C. Action category, all it says is action A can be performed on data items in category C. Banned actions, action A cannot be performed. And authorizations is where action A is authorized on data item DI generated by device D. And of course, you have prohibitions where actions cannot be performed. And then in some cases, it's undetermined because you don't have enough information. Okay, so then we came up also with axioms. What is really interesting about this is that we incorporated this work, Gopal, into the Alvaro's Science of Security Lablet, and NSA Vanderbilt is the prime contractor. They really like this piece. So this has gone in, and so when this task comes, we'll be doing more work on that. So there are 4 axioms which are derived from the category-based model, which I haven't really discussed the details. So the first axiom is saying that, very briefly, for every device, for every A, for every data item, there are categories C and C prime, right, where if the C is a subset, category C is a subset of C prime, any actions that you can allow in C prime, it can also be allowed in C. And the prohibition actions is the opposite. If something is prohibited in a subset, then it will be also prohibited in the superset. It's obvious. And then in some cases, we are saying when it is undetermined, right? If it's A and B, if they are contradictory, okay, we need more information. So there are exceptions. Now, that is the axiomatic semantics. We have also defined a operational semantics based on rewriting systems. So rewriting systems and lambda calculus essentially defining functions for each of these axioms, and these functions are the ones that are going to implement these policies. Okay? So here's an example, DC1 prime, which is the rewriting operational semantics for the axiom DC1. So I will provide a short example, and that is rental prices, right? Trucks are going all over the place, inside UK, outside UK, or inside US, outside US, and they are transmitting information. So what we are saying is when trucks cross the border, we want to monitor them. Then we collect the data. We collect the data from the trucks, and only if they are going to a foreign country. If they are in our home country, we do not collect the data. Okay? So what is our policy? Assuming a truck device has just one element, one operation, very simple example, transmit. The categories, you can be either home or you can be abroad. And you can transmit data abroad. That is permitted. ACA is permitted and BACA is prohibited. And you can transmit data from home, but that is prohibited. So that is the operation, the axiomatic semantics. And now we have defined the operational semantics, where DICA, where is you are transmitting data, right? If in the UK, so ACA means if it's broad, you can transmit. If it's not, if it's at home, then you do not transmit. Okay, so what are the actions that you can perform? Now, why is this important? Because now all of the tools that are being developed now, some by us and some by others, we can use that, for the implementation of the policy. And so that's for, and so we discussed this with NIST. And one criticism we are getting is that the implementation efficiency. How can you have a model that's going to handle everything? And if you have millions of categories, isn't it going to be really, really difficult in terms of efficiency? But we also want to do for data sharing. But again, this is the only sort of formal model, because what NIST has done with their ABAC, attribute-based access control, it is not sort of a formal model. Okay, it's somewhat ad hoc. Okay, so now I think I just want to briefly mention this, okay, because this is really what I'm going to talk about. I'm a team member with Latifer and Murad's team. So I sort of set the direction, and you can see from this article here that Chris Clifton talked about. In 1996, I said, look, now we are starting to talk about data mining. Everybody is getting very concerned. We have the World Wide Web. What about security and privacy, right? Because of all the data that is being collected. So I believe I was the first to introduce it in the IFIP keynote address in 1996, and then later PAKDD in 1998. And essentially, this is Murad is sort of the world's expert in this now. You take the privacy preserving. You take the original data, perturb it, randomize it, and then you get the perturbed data, random data. Okay? Whole idea is to have the new distribution as sort of close to the old distribution as much as possible. So we built a community when I was at NSF. That's the one advantage when you go to Washington. I'll very quickly mention that towards the end. Okay, so I come here, and so we start this project on data mining for malware detection. Okay, so I'm going to skip this because of a lack of time, because this just shows essentially the whole process, right? You build models. One of the things that was kind of new at that time was that the models are not static. We are continuously updating the models, ensemble of models. And the first paper has several of our tools. And the second paper is something, it's not mentioned here, but this has given us a lot of visibility, patent, and with Urbana-Champaign. So this is not really very relevant to what I'm going to talk about. So very quickly, with my student, Dr. Pavin Pallabi, we designed and developed, so my sponsor, our Air Force, said, insider threat, huge problem. Okay? What are y'all going to do about it? So we then designed and developed, right, supervised and unsupervised learning techniques for insider threat detection, right? So an ensemble-based means not just one model, collection of models put together. And so models are continuously getting updated. So this is sort of the picture, and I'm just going to briefly touch because, again, I'm just a contributor here. And what we are trying to do here is actually, we are taking chunks, and every chunk is trained with a particular model. It could be support vector machine. It could be nearest neighbor. So every chunk is trained, and then we collect all the chunks and develop a new model, and all the existing models, put it all together, merge them, develop a new model, and then we do the testing. And then, of course, so this is sort of the approach, both supervised and unsupervised. Supervised, actually, we have the ground truths, and that's obvious. Unsupervised is a little bit cheating because it's sort of semi-supervised in the sense that, while we do not have ground truths, for the unsupervised, we are looking at system sequences of system calls. So what we are saying is normal users have repetitive sequences of commands, and sudden deviation from normal behavior could raise an alarm. But these are millions of sequences, so there is an efficiency problem. So what we do is we use the Limpel-Ziv-Welch algorithm. It's already there. It's not our algorithm, to do the compression, okay? And so that we throw away sequences that may not be meaningful and collect only the sequences that are meaningful. Of course, some useful stuff could get thrown out. So due to lack of time, I'm not going to talk more. This is sort of a little bit more on the construct the quantized dictionary, and then some of the lessons learned, okay? So the last piece of work I wanted to discuss is this adversarial machine learning. It is becoming one of the most important areas in cybersecurity. Why? All these machine learning algorithms, what happens if these algorithms are attacked, right? It can do all kinds of crazy things. So here you have a support vector machine. The blue parts are good, right? The red parts are bad, attacks. But if your algorithm, support vector machine, is attacked, what happens here? The red becomes blue. The attacks are stated as good stuff, and that's very dangerous. So Murat and I got this started, and then Murat kind of ran away with it. He's now very well known in this area. Solutions and threats. So what we are saying here, and this was Murat's brainchild, let us look at incorporating the attacker's behavior into our machine learning models. Okay? So we can do it during training time. We can do it during testing time. So let's put some attacker stuff, right? Attacker could change patterns. Attacker could throw more packets or thwart us by putting spam. All that is taken into consideration. Now, there's some challenge here. So what we looked at two attacks. One is free range. So free range meaning adversary can move malicious data anywhere within a certain range. But restrained attack, adversary is getting a little bit craftier. So I'm not going into the details. It's in our paper. A restrained attack, adversary would be reluctant to let data point move far away from its original position. Okay? So then we designed support vector machines for each of these attacks. We looked at two attacks, and that was, so after that, Murat has done a lot more work in this area. So I was involved in this for the initial part, funded by Army. And then we designed the support vector machines. So this, I believe, is for the first attack. And you can see in the first, you have positive and negative, right? So all the red parts are negative, I believe. The green parts are positive. But once we do our adversarial machine learning, right, So more of the things that are going as negative, right, are actually positive. So it's catching more attacks. So this, our army, so I'm going to talk a little bit later about my motivational part. So this is really going to be crucial, because this is where lots of funding is going to be put in. And thankfully, you know, because of Murat, this work is continuing for us. Okay, so these are some of the lessons learned. Okay? Now, I want to start a little bit with the motivational. DT said, make sure you have research problems, Dr. DT Huynh, who was my former department head. Okay, so let's go back, right? Designing and developing secure data management systems, still there, because database systems are everywhere. We've got to worry about all what I talked about in 80s and 90s, plus guess what today? Malware. Okay, so whatever stuff that Latifa is doing and whatever stuff that Murat's doing, all that has to be integrated. It's challenging, very difficult. But we can't say, let's forget about it. Let's only do one piece. So what Murat's doing is really great, but I don't think that's enough. What Latifa is doing really great, that's not enough. What I'm doing is really great, that's not enough. We need to combine all three pieces, and that is the challenge. I don't think we really know how to do it, unless maybe Murat's brilliant, so he might know. I don't know, but I don't. But lot of stuff. Complexity of the inference and privacy problems, which I started 1990, and it's still there. And I think some of the breakthroughs are coming in the complexity, unfortunately not by me, but the Harvard Data Privacy Group. Okay, fortunately Murat is part of the group. So at least UTD can continue to. Dependable data management, I'm not doing any work here, but we have, he hasn't shown up. Kong Liu, very well known in real time. Okay,